Hi, everybody. This is Francesco Caravelli, and I'm one of the organizers of the school. Um, I First of all, I would like to thank you for participating in the school, and both from me and from Lyubov Tukina, the other organizer, and also I would like to thank the other lecturers for actually participating in the school for free, basically. This is a bit of an experiment, as you might have guessed, as um, it's rare in complexity that there are these schools for free online. So very good. What the set of lectures I'm going to give, the 2 hours more or less I'm going to discuss about are about is basically an introduction to spectrum methods in complex systems and spectrum methods in general. And this is an introduction for those who don't have a mathematical background. Uh, so for some of you might be actually fairly boring, but there are some non-trivial statements that you'd see or non-trivial point of views in the set of lectures. Um, Something I should mention is this is based on a set of lectures I gave in Sydney a few years ago. You'll find some reference to some exercises. If you go to my website and download the file tutorial.zip, inside there are um, exercises written in MATLAB that you need to work on, or if you want to. There is going to be a number associated with exercise for familiarize with the topic. Motivation for a spectral approach. It is a personal perspective, but I find eigenvalues problem very elegant. If you can map your eigenvalue problem to a problem of interest that you're studying, then there are very many techniques available for either solving the problem computationally or to solve it analytically. In general, it finding or calculating eigenvalues, it's a fairly uh, quick thing on a computer in the sense there are very efficient algorithms available. Um, Also, it's good to know that uh, how to solve or how to treat an eigenvalue problem because sooner or later, even if you are not mathematical oriented person, you will hit an eigenvalue problem if you do research in complexity. I also another motivation is spectra are fairly central to many topics that are in the field of let's say complexity science, and in general to many not only complexity but to other disciplines such as physics, engineering, mathematics in general, economics, and so on and so forth. Um, there are also some non-trivial, let's say, not complete trivial statements that one can make and to connect, say, spectrum methods to behavioral polynomials or statistical mechanics. So in general, it's very central and it's good to know the basics. Of course, you should know by now that there is me and Duba have been working on this book for a while. This is an advertisement, basically. This is a work in progress again. There are certain sections that are not finished, but you can actually access it online even if we are still working on it. The outline for this course or this lecture, it's 2 hours, so which the first hour is going to be a quick introduction to eigenvalues graphs, walks, data solved, and to pseudospectra, which is an advanced technique. And the second hour, or rather half an hour, is going to be more around applications. So here I'm going to define right and left vector matrix multiplication and matrix multiplication vector dot product. Um, these are basic definitions. So if you have a matrix, you can apply it to a vector by summing over the indices, and of course you can do the right and the left vector multiplication. If you add two matrices, you can multiply the two matrices by summing over the intermediate indices. In general, the operation is not symmetric. So if MQ is not equal to QM, um, so it's not a commutative operation. And of course, also there is a vector dot product that we're going to use, which is basically if you have two vectors, you can take the dot product, which is a scalar, and the sum is a sum over the product of the two vectors element y. Um, Apart from the commutativity, which is absent in the multiplication of matrices, you still have associativity. It is a linear operation, so if you multiply by a matrix by a scalar, then the result of the product is going to be a scalar, and so on and so forth. Of course, it's distributive in the sense that you can, if you have the sum of two matrices and you multiply, it is the same as the sum of the two uh, products. One comment about notation. I'm going to mention several times the tensor product for vectors. Um, I tend to have use two notations. One is the first here in the slides, so x cross y, or I usually I also use this other notation where I ex make explicitly the transpose of the red vector. Just for those who don't never saw this, suppose I define the tensor product of two vectors is a matrix, and if you apply it to a vector z, then all it does is basically spits you back the vector x, which is was the one defined on the left of the tensor product, multiplied by a scalar, which is the dot product between y and z. Here we define that the eigenvalue problem. So given a matrix A, we call eigenvector a vector such that if you multiply A uh, by x, then it gives you back the vector x multiplied by a scalar, and this is an eigenvalue. For instance, if you in this dot product here, if you x by definition is an eigenvector. In fact, um, you can always multiply um, apply m to x, and it's going to give you a scalar product between y and x and multiplied by x. Of course, you can have left and right eigenvectors. For symmetric matrices, these are the same and they have the same eigenvalue. For non-symmetric matrices, this is not the case. This is one example of one situation in which I'm going to use the tensor product. A matrix A, if you have a eigenvalue decomposition, can be written in the following form. It's a weighted sum where the weights are the eigenvalues of the tensor product between the eigenvectors of the matrix A associated with that specific eigenvalues. The first formula is true for symmetric matrices, um, and it's very often useful. This is the same as the diagonalization of a matrix, but you also can have a non-symmetric version of this statement where you replace basically the tensor product of the left eigenvectors with the actual left eigenvectors of the matrix A. What distinguishes from a matrix that can be diagonalized by a single set of eigenvectors is basically normality. Normality is defined as the given a matrix A, it is the commutator between A and so actually there's a sign error here, but it's defined as the commutator between A and the adjoint of the matrix A. If this quantity is zero, then the matrix A can always be decomposed as the first formula in this slide. Okay. Examples of matrices are normal, for instance, are symmetric matrices. Other examples are Hermitian matrices, or matrices such that A adjoint is equal to A. And both these matrices, for instance, have satisfy they possess a spectral theorem, meaning that the matrix sigma here in this slide, which is a diagonal matrix where the eigenvalues are, is a real matrix, meaning that all the eigenvalues are real. Examples of matrices that satisfy spectral theorem of this form, meaning that they can be diagonalized by a complex eigenbasis, but where the eigenvalues are not real, are skew Hermitian matrices, for instance. These have eigenvalues that are only complex, like actually more than complex, are only imaginary without a real complex part. If you have so the statement about A can actually be made also about um, sorry, let me rephrase. You can matrix inverse is defined as the matrix such that M inverse multiplied by M both on left and right is equal to the identity matrix, a matrix made only on one. If you know the inverse, if you know the eigenvectors, the eigenvalues, then it's easy to calculate the inverse if the eigenvalues are non-zero, which is simply you in this first equation here, you replace sigma with sigma to the -1, which is basically the same as saying the inverse the eigenvalues. Take it 1 over the eigenvalues. And this is a way of calculating the inverse. Something I wanted to mention is the connection between eigenvalues and polynomials. There's a huge literature on these, how to make this connection explicit. And for this slide to be understood, you need to know what is a determinant. So I assume you know it. I'm going to describe it a bit in details the properties of the determinant. But for the determinant of A minus lambda I is nothing more than product of eigenvalues of this matrix within the determinant. The statement of the connection between the eigenvalue problem and the polynomial is the following. If ax is equal to lambda x, then this means that a minus lambda I must have an eigenvalue which is 0, because this is the statement that there is a vector x such that this applies to the vector x. Basically, this is going to have an eigenvalue. It's going to give you 0, which means it has an eigenvalue 0. If this is true, the determinant, which is the product of the eigenvalues of the matrix, then has to have an eigenvalue 0, and this implies that the product is 0. Okay, but now you can write the determinant as a polynomial in lambda, and this implies that the eigenvalues of a matrix A can be obtained via the roots of the characteristic polynomial defined as a determinant of A minus lambda. Okay, so many results on the properties of eigenvalues of matrices can actually be inferred via the properties of the polynomial per se, or the characteristic polynomial. These, for instance, have several properties. I mentioned here basically the derivative of the characteristic polynomial is the characteristic polynomial itself multiplied by the trace of the resolvent. Okay, we're going to discuss this later. For instance, certain traces of traces and determinants, since we're gonna use it. The determinant again is the product of the eigenvalues of the matrix A. Meanwhile, the trace is defined as the sum of the eigenvalues of the matrix A. Can be defined at least as in terms of eigenvalues in general, but there are also other definitions. You probably should know this. They do have some properties. For instance, the determinant of AB can be written as the determinant of the eigenvalue of both the matrices. And given this rule, basically it's easy to show the determinant of the inverse is 1 over the determinant. One comment is the determinant of A plus B is not easy. Usually these are not well behaved in this sense. Meanwhile, it's not trivially the sum, or let's say the product of the sum of the eigenvalues. Meanwhile, the trace of A plus B is trivial in the sense it is exactly the sum over the sum of the eigenvalues of A and B. Again, the definitions can be made in terms of eigenvalues only if you know them. Um, so the next two slides are just to show that there are a lot of results or formulas you can find online about the properties of determinants and its derivatives. For instance, here I define the product um of the derivatives of a certain matrix X and know the determinant. These are you can find them online, and all I want to say is, for instance, like this, there is a beautiful book or cookbook rather online called the Matrix Cookbook. It's fairly well known in computer science, in particular among those doing machine learning. And you can find basically these formulas here in that book. For instance, this is an interesting result. The second one, determinant of I plus epsilon A can be written exactly in terms of traces and determinants, which is a fairly non-trivial result for epsilon small at the up to the second order. And also several results about the traces and the traces of the sum matrices. And this is just to say there are several results that are known about the derivatives of quantities based on matrices, and you can find them on this book. Um, one known result is in general, well, not always eigenvalues are well behaved. If you take a matrix and you sum another matrix to it, in certain cases the eigenvalues may stay close to where they were before, but sometimes they don't. They actually may move away. One way to check this is via this theorem called Gershgorin theorem, and basically this is one way of bounding the position of the eigenvalues in the complex plane, and it works as follows. Um, Define Ri as the sum over the rows uh, of um, of A without the diagonal element. Okay, if the matrix n by n, you're gonna have n of these quantities. Then given these quantities Ri, define the domain Di as the circle centered on the diagonal element Aii. So I'm gonna have n of these um, bounded in the complex plane by Ri. So in the complex plane, this is gonna give you a bunch of circles. Okay, the union of all the circles is called the Gershgorian domain, and this is one way to check or to bound the eigenvalues, given the knowledge of the nth element. Usually, these theorem is fairly loose unless the matrix is sparse, so only few elements um, are non-zero. But there are other options that you can use. For instance, in the book there are other bounds you can use. As an example, I mentioned here the Ovalso-Caccini Farn theorem, Schur and Weil theorems and inequalities that actually give bounds on the eigenvalues. We're gonna see more bounds later, but I wanted to mention this. Go and look them up in the book. Another thing to mention is eigenvalues do not define exactly the matrices. So if you have a set of eigenvalues, you might have several matrices that actually are generated that have the same eigenvalues. One way to see these is by using the characteristic polynomial as follows. Consider the matrix M, okay? Then introduce another matrix P, and take M and multiply on the left and right by P and P minus 1, assuming that P is invertible. Then it's not too hard to see it actually. P or lambda for both matrices is the same, and the proof is actually provided in the series of formula at the bottom, and it relies basically on the properties of the determinant, and basically shows that P or lambda is the same for both the determinant of A minus lambda I, and for the determinant of P A P minus 1 minus lambda I. And basically this is you can prove it by inserting a 1 as a product and as a property of the determinant. So in this sense, given given a certain set of eigenvalues, you have a whole, or rather a matrix, you have a whole set of class of matrices that actually have the same set of eigenvalues just by generating all possible p's that are invertible. So it's a huge class. So here we go in the section and we talk about diagonalizable versus not diagonalizable matrices. And to see the importance of what the difference between the eigenvalues of matrices that can be diagonalized, those that are, or rather, symmetric or non-symmetric. Here we're going to discuss actually one example of non-normal matrices, matrices for which eigenvalues can move a lot. And for instance, consider a random matrix, which is basically a matrix whose elements are random. Let's say between -1 and 1. If you enforce that the eigenvalues satisfy the matrix is symmetric, then it is known that the eigenvalues, the distribution of the eigenvalues satisfies the unit semicircle law. Okay, and for instance, the lectures by Jacopo Grilli, you go into details into random matrix theory, so I'm not stay here to discuss. But you see that this is, for instance, a numerical result. You see that the distribution of the real eigenvalues for this matrix is actually fairly well behaved and well known. It's called Wigner's semicircle law. Now, release the fact that the matrix is not symmetric. In this case, the spectral theorem is not valid anymore. So what does the Gershgoring theorem says? And basically, you see that via quick calculation, that actually the eigenvalues can be all over the place. And so you lose a lot of bounds on the position of the eigenvalues already. And it's to show that actually eigenvalues can move a lot if the matrix does not satisfy the normality condition. So there's also distinguished matrices. Matrices can be diagonalized or non-diagonalized. What happens if a matrix cannot be diagonalized? So despite the fact that the matrix cannot be diagonalized, it can always be reduced to a form called Jordan normal form. Again, if you have a mathematical background, you should have studied this. But remember that for the matrix, for say asymmetric matrices, we could always reduce the matrix via the work by the by calculating the eigenvectors to a form where J is diagonal. The most general version of this is actually the Jordan normal form, and it's basically, instead of having diagonal matrix, you get a matrix which is block diagonal, and so, and then the blocks are called Jordan blocks. And I just wanted to mention that despite the fact, it is good to know that this can be done. For the details, you can go and look pretty much in any linear algebra book, or if you want to see the short version of this and the connection to the Cayley-Hamilton theorem, which is the last formula there, you can just go and look into the draft of the book. Another thing which is useful to know is if you don't want to reduce to Jordan normal form and you really want to have diagonal decomposition, let's say similar to the one with left and right eigenvalues before, you can use what is called a singular value decomposition. Okay. In general, the singular value decomposition gives you diagonal matrix gamma, sigma, but instead of having the eigenvalues there, you have the product, or the squares of the eigenvalues of m. And this is because even if this is basically on the following idea, and again, for details, I suggest you go and look in books. It's good to know though, that even if you cannot diagonalize m, okay, you can always diagonalize m, the product of m and then m transpose, or and the product of m transpose m, because these are symmetric matrices. Okay, this is easy to prove. Okay, and usually the single value decomposition can be used as a matrix compression because the sigma is going to be only positive matrix elements on its diagonal. If you have some elements that are very small in this matrix, it is to show that you can just drop them and you're going to have a compression of information for n. So it's usually a way to reduce the size or remove information or noise from a matrix or from a set of data. Okay. Again, I'm not going to go into the details of these, but it's good to know that this is exist. You can use, and so here this is why I introduce single value decomposition. The single value decomposition can be used to calculate the inverse. Okay, where suppose the n does not have an inverse, which means some elements, some eigenvalues are non-zero. How can you calculate pseudo inverse? Okay, what you can do, you can invert sigma, the elements in the diagonal matrix sigmas, those that are non-zero. And this is gonna is your definition of more parent inverse, which basically it's nothing more than an inversion in the subspace of vectors that are not in the kernel of the matrix, which means it's not in the set of zero eigenvalues. Um, Here is another slide about properties of eigenvalues, and this is about interlacing. Um, you can uh, you can use commutators to have to infer properties of eigenvalues. So, for instance, suppose that the matrix A has a certain symmetry, and by symmetry I mean this, for instance, useful in quantum mechanics. Suppose that P and A commute, which is exactly what's written in the first equation here, and that you know the eigenvalues of P and A. Okay, then you know that the eigenvalues of P and A, when they are put in order, they must interlace, which means there is a property like the one of the second equation in the slide. And very often you can use this because if you know that the matrix has a certain symmetry, which means it is commutes with a certain set of operators, then if you know the properties of these operators, you can always bound the eigenvalues of the matrix. Other bounds that are known about the eigenvalues are these in terms of the singular values of the matrix M. The singular values are those that we described in this decomposition here, and are the diagonal elements of sigma. Suppose that lambda eigen are the eigenvalues of A and sigma the singular values, then you have these properties between the singular values and the eigenvalues. I know I'm going fast. If you have questions about these, you can just look them up or ask me questions on the Google group. So from here on, we start to introduce graphs, and we're gonna take a break, and so okay, you can breathe. And this is the first part, the first lecture.